done with CNN. Okay, I just want to show you before we close the CNN discussion. Just show you a few CNN variant models. Okay, in that case, you will know how to design your own CNN architecture. Okay, it does not have to be just download some of the CNN models. The good thing, but anyway, let me just summarize one more time. Okay, for the architecture first. About the convolution layer, for the user, you need to determine what should be the number of the convolution layers, and for each layer, how many filters. Okay, how many filters? Usually, we will use tens or even 100. Okay, it's hardly just use 1 or 2 or 3. Okay. Then the filter size. If you have no idea, some of the CNN models, such as VGG. The one you use for your assignment, you use 3 by 3 all the way for all the convolution layer. Okay, and the number of strides for the convolution layer, the usual way is we set up stride with 1. Okay, if we want to maintain the input size, you can use zero padding, okay, to maintain the original size. Otherwise, after each convolution layer, the input size will getting smaller and smaller, okay? And one of the very important selection will be the activation function. If you have no idea at all, usually just go for red rule, okay? But it does not have to be the best way. Nowadays, a lot of use Gaussian explanation, okay, or a kind of liquid red rule, okay. That will be the one that you can choose, okay. And then you can determine if you want to go for the pooling layer, okay. Don't pay too much attention on it. Just use the default 2 by 2, okay, 2 by 2 with a stride of 2. But some of the convolution layer, it will split after the convolution layer, it will apply maximum pooling and also mean pooling at the same time, okay? And finally, they will combine together and do more convolution, okay? So that you have a lot of choice, okay? You want to do the normalization, go for batch normalization. Let's normalize, okay, along the sample. Last week, I also mentioned you can go for the their normalization, okay? So you normalize the value for each sample, but you take the mean and standard deviation for all the features, okay? That will be the difference, okay? And for imaging, then you go for the flatten to convert the 2-dimensional, okay, input to 1 dimension. And then usually you will go for 2 or 3, okay, dense layer or fully connected layer. For that, you need to determine how many dense layer or fully connected layer, and for each layer, how many number of nodes. This will take most of the parameter because it's fully connected, okay? And also, you need to determine the activation function. For classification, the output layer, you will take sigmoid, okay? For regression, never use red rule, okay? Never use red rule, especially the output or the estimate, the value could be negative, okay? And then for the fully connected layer, you can determine what should be the percentage for the dropout, okay? That can prevent overfitting, okay? Then the output layer, if for classification or for response, then you need to determine the number of classes. For regression, it means what? Most of the traditional regression model it will take multiple input, but only one single output. Okay, but if you go for the deep learning or neural network, you can have a multiple output. It does not have to be one single input with the same input. Okay, you can input a set data, but the output response can be Y1, Y2, or anything else. Okay. Okay. As I mentioned, if for classification, you will go for somax. Okay. And then this another important parameter to determine if you can train the model, which is what should be the loss function. Usually we simply go for a mean square error or cross entropy. Okay, we use cross entropy, no matter it's for classification or even for segmentation. Okay, if for segmentation, if each pixel it can be a pixel wise. Okay, you can consider it as a pixel, and the output can be 0 or 1. Then in that case, usually you can go for the binary cross entropy. Okay, what should be the ultimate algorithm? If I have no idea at all, just simply go for the stochastic gradient descent or add. If both fail, it might fail. Okay, no matter what you change. What I'm saying could be wrong, but most of the case, just go for SGD and add. Okay. And the most important thing is the number of epochs, okay? How long should it go? And the most important one will be the learning rate, okay? 学习力最重要 okay? 学习力最重要 okay? The batch size will help you to converge faster, okay? And even help you to get the better result, okay? So anyway, the minimum batch size is 1, the maximum batch size will be the whole data set. But usually we don't use the whole data set as the batch size. Okay, you will grab it into a small batches. Okay, that's all the parameter to build up the architecture. Okay, so now we can see a few. Okay. This is the development or the history of the development of CNN in the early day raccoon, okay, called NET, okay, developed in 1990. In the early day, this is used to recognize the handwritten, the signature in a check, okay, 那个支票签名了，他是在看那个支票签名。Okay, then comes NSNet, a breakthrough, okay, for ImageNet, okay, and the very first one is GPU. And then after that, they have the more famous one will be the Google Net, okay, Google Net, okay, called Inception. Okay, I will show you the model, Inception. And then VGG Net, okay, this is also very popular. Okay, nowadays, okay, a lot of models use VGG as the baseline, okay, and then comes the residual net. It can go up to 150 something layers, very deep. Okay, I will show you the model. Okay, and then you can look for some of the more details about the CNN. Okay. Nowadays, the state-of-the-art or up-to-date CNN model will include, as I mentioned, that will be part of your assignment number 4 called Convolutional Next, okay, developed by Facebook, okay? And the other one is Convolution Mixer, okay, Convolution Mixer, okay? Developed by He Kai-Ming. Okay, He Kai-Ming. Okay, I will introduce these two. The other one you can look for is efficient net. It will help you to determine what should be the input image size, what should be the number of layers, and what should be the number of filter or the width of each layers. Okay, so that it will can be learned efficiently and also very effectively. Okay, called efficient net. Okay, and also there's another. Okay, I'm not include here called mobile net. Mobile, especially used for mobile phone. Okay, so that it will consume a very small memory, and also will require less computational power. Okay, but anyway, let me say something about the residual net. Okay, the residual net. Okay, here is okay. I'm looking more which one would be much easier for you to. Okay, this is the original CNN model. Okay, you can think of it as a block. Okay, a CNN contain a little block. The first you have this does not have to be the original input image. It could be a feature map from the previous layer. 这个 X 不见得一定要是最原始的影像它可以是上一阶的的那个 feature map. Okay, then you go for the convolution layer. Then we apply red rule or any activation function. Then we go for the convolution layer. Then we get the estimate output. Okay, and then this can be an input to the next layer. But for the residual net, a block, it goes like this. When I say block, this means this block can be repeated. Okay, again and again. Okay, this block, well here, just like the plane layer. We have the input. Okay, the input could be the original image or the feature map, just like this from the previous layer. Then you go for the convolution layer, redo convolution just exactly like the plane layers. But the difference is like this. It will bypass. Okay, the input X will bypass the convolution layer. Okay, and after that, we actually sum up. Okay, the output and plus X. Then that's the reason why we called it. Okay, this is the residual. Okay, this is called the residual. Or we can think of the residual is H minus the original input. What is left is called residual. Okay, it's called residual. And then to estimate the H, okay, just like the plane CNN will be much more reliable to estimate by the residual plus the original, not the original, I mean the input X, okay, the bypass, just like this. So in this case, if X fail for the convolution or activation function, because the gradient vanished, 因为那个梯度会消失. But when we bypass these two operations, we still can recover something here. That's the reason why residual can go up to more than 150 layers. Okay, otherwise, usually, it won't converge at all. Okay, so that's why it's called residual, because the output is the residual. Then we plus X that will equal to the estimate H. Okay, so we don't calculate H from the plane layer because you might encounter the gradient vanish. Instead, we bypass these two convolution layers. And after that, we add it back, okay? And then you go for the next convolution block, okay? Or called residual block. That's the idea, okay, of the residual. And it is a breakthrough, okay, for a very, very deep convolution layer. For VGG, as I mentioned, usually the one you use for assignment number 4 contains 16 layers. It has another version. It contains 19 layers. The same here for residual neck. You have a residual 34, I think. I'm not quite sure, 34. And it can up to 150 something, okay? And you can use the pre-trained model. Pre-trained with the image neck, as I mentioned, it has more than 1 million images and a total of 1,000 classes. So you can use the pre-trained model as the initial parameter, and then you can train your own data set. Okay, that's the idea. You can make it more efficient. That's one of the purpose for your assignment number 4 is to see if train the model from scratch or use the pre-trained model, okay, and for your own application, which one will be more effective and more efficient. Okay, that's the residual net, okay, residual net, okay? Okay? Now here's another model based called Google Net, but it has another name called Inception, okay, Inception. It built a wider network rather than a deeper network. For residual net, they use a very deep, okay, very deep convolution layer. But for inception, it uses a wider layers, okay? What does it mean by wider? Here's the idea, okay? Now, suppose this is our previous layer, okay? The input from the previous layer or from the original image, that'll be fine. Usually, then we go for the convolution. You can select 3x3 or 5x5, but for inception, you will split into 1x1 convolution, 3x3, 5x5, or you can use 1x1, 3x3, 7x3, which means you can use multiple convolution. Okay? Now, a small convolution will extract the details feature, but a larger convolution can help you to extract a more global features. That's the idea for inception. Okay? Now, you might wonder, what is 1x1 convolution for? What is 1x1? You can understand 3x3, right? It's 3x3. You can understand 5x5. This is 5x5, 3x3. But what does it mean by 1? Just one element. So what's left for? If I use 10, it means what? The channel for the next input will have 10 channels. If I put 20, which means the next layer, the input for the next layer, you will have 20. So what is the purpose for 1x1? It's right here. If you put K, it means the depth will becomes K. So usually when you go for 1x1, which means you try to reduce the channels, it must mean in the previous layer, it must be, the depth is very high. For example, you can use 500, can be up to 500, the depth for the data set. But then if I put just 10, it means what? For the next layer, because 1x1, the size, you won't change the size, right? The size. If the size is 100 by 100, because the convolution is 1x1, so the output size still will be 100 by 100. but the depth will becomes which means you will reduce the channel, okay, from a very deep channel of the input size to a very small size. So it means what? So actually, the 1x1 filter, should be 1x1, for this case, should be 1x1 by 10. It means what? This is your filter. You have weight 1, weight 2, and up to 10. So it simply calculates the linear combination for some pixel, okay, along the depth, along the channel. Everyone follow me? It's a linear combination. You put all the information at the same location in different channels. So it's a linear combination. So whenever you look for 1x1, okay, you don't need to doubt why it's 1x1. It looks like it do nothing, but you think of all the linear combination along the channel, okay? And one of a very important, okay, task is to reduce the channel size. Okay, we can reduce the channel, especially in the previous one. You have, especially for this one, okay? So anyway, for the inception, you go for 1x1, 3x3, 5x5, and also you take 3x3 max pooling. You use the 3x3 max pooling, okay? For this one, you don't need any parameter. There's no filter, but it does not use a 2x2, it uses 3x3. And after that, you do the concatenate. That's another terminology. What does it mean? Concatenate. For this case, okay, for this case, if I go for 1x1 with 20, okay, I have 20. Suppose I use 20, 1x1, okay? And 3x3, I use 50. And 5x5, I take 30, okay? And then the pooling, okay? You take pooling. And suppose the original size, okay? Suppose the original size, because it's pooling, so the size will be the same as the previous layer, right? Okay, suppose the input, okay, the depth, I assume the depth is 100. So you will have a 100, okay, 100, okay? The depth is still 100. After the concatenate, okay? After you do the concatenation, what will be the depth? To do the concatenation, first you have to make sure all the sides are the same, okay? You need to make sure all the sides are the same. You can go for the what? Padding, okay? Suppose you have padding, or you can resize. The size must be the same. After the concatenation, what will be the depth? What will be the depth? Here, when I put actually we don't do the addition, okay? No, we don't sum them up. We just, it's so-called concatenate. We just put them all together. What will be the depth? Here, it will be equal to 20 plus 50 plus 30
200.
plus 100. So the depth will become 200. So everyone knows what I'm saying? This is a concatenation, the so-called concatenation, okay? So you will put all the information, like this case, from a very small filter, okay, or a very large filter, or we don't use the filter at all, and we concatenate them together. So after that, then the depth will be very, very large. So usually, what will you do after that? You will go for one by one convolution one more time to reduce the depth. For example, if you go for just 5 and one by one, okay? I'm sorry, should be one by one. Actually, this one by one, the depth should be what? The depth should be what? 200. For this case, should be 200 because the size is 200. But we use 5 filter like this. Okay, so after that, then the depth will become just 5, and maintain the original input size, okay, in the two-dimensional space. That's the idea, okay? So anyway, the inception allow you to extract the feature in the fine or in a very small region, and also you can use a very large filter, okay, to represent some global features. That's the idea, okay? That's the idea about inception, okay? Co-inception. You can do this, or you can change it, okay? When you download the Google Net or Inception, you can change 5 by 5 to 7 by 7, for example, okay? Okay, that's the idea, okay? That's the idea. And I also explain what do I mean by concatenation here, okay? You can go through it. 好，记得哈，这个假如真的要叫中文的话，我不知道，你这样问我，我会说是串接，把它们串在一起 ，OK， but nothing to do with the mathematical, okay, addition， 好，跟加法没有关系，不要把它和在一起。But anyway, before you go for the concatenation, you need to make sure, okay, so for each branch, they have the same size, okay? They must have the same sizes, okay? So that's the implementation, the actual way here, okay? From the previous layer, you go for one by one first, okay? No matter what, you go for one by one, okay? And then you carry out 3 by 3 convolution, 5 by 5 convolution, which means the first you go for one by one, you try to reduce the channels, okay? You try to reduce the channel first, okay? Try to reduce, okay? And then you go for one by one, 3 by 3, 5 by 5. And after the math pooling, you carry out the one by one convolution. Also, you try to reduce the depth. And then finally, you concatenate all these 4, the output of these 4 branches. That's the idea. 好，就是说一开始啊，它不会直接 they don't go for 3 by 3 immediately. Usually they go for 1 by 1 to reduce the channels. Okay, and then you carry out 3 by 3, 5 by 5, 1 by 1 to extract the fine details or the global representation. Okay. And why you go for the max pooling? Because you try to maintain the original information. Okay, they don't try, and finally they concatenate they all together. So all the information here, some channel will preserve the details information, right? And some channel will preserve the global representation. And some channel will maintain the original signal, okay? And then we go for the next, okay, convolution layer. That's the idea, co-inception, okay? So you will have a different performance, okay? And also up to your application, you can select just simply go for residual. Residual neck, you use a very deep, okay, architecture, or you use a rather wild layer. See that? This is called wild， 它比较宽，比较胖。Residual 呢是比较瘦，可是很长，啊，很深，两个不一样，啊，两个的想法不太一样。OK。Okay, so that's the idea for inception. And also for the convolution next, okay, I already mentioned that before, but let me just re-summarize one more time, okay? Here, this is the residual block, okay? One of the residual block, convolution, and convolution, okay, that's another block. And here, what you still call residual neck is bypass, okay, bypass. Okay, the input from the previous layer will bypass all these three convolutions here, okay? And then you do the addition, okay? You do the addition, not concatenate, okay? 这边是真的做加法啊 ，you actually add them together, okay? So first you go for the, you use a 64 filter, okay, 64, and then 255. But for convolution layer, the block, then you use 96, 384, and 96, okay? So it's so-called the inverse bottleneck, okay? The block in the middle has more filter, okay? It's filter, okay? 384, but it's 96 here, 384, okay? 96, okay? Usually, well, you will go like this, okay? 384, 96, and then 384. Okay, this will becomes the bottleneck, called bottleneck convolution, and this inverse bottleneck convolution. Okay, and then after the first convolution, you go for their normalization. Okay, L means layer. Okay, it does not use batch normalization. It tries to mimic what is the operation used in the transformer, okay? That's the one original transformer called swing transformer, okay? That's because it uses 96, okay? 96 and 384, okay? And then 96. So it is an inverse bottleneck. So for the CNN, you use the same strategy. Okay, and also it replaces the batch normalization with layer normalization. And the residual net, you use batch normalization and red loop, okay, activation function. Now it changes to the Gaussian exponential, okay, change. That's because why you replace it, that's because the transformer use this Gaussian L, okay, activation function. So just to replace it. And on some test image set, it claims convolution next perform better than the transformer, okay? The transformer, because it's up-to-date best model, okay, deep learning model. And now here comes the convolution next, okay, block, okay? So that's the very first difference. And you will repeat the block okay? You will repeat the block just like the residual net, okay? That's another reason why Carlos does not like this at all. Okay, when you run it, you will see it's time consuming to train the model. But because the baseline for the convolutional net is still residual net, okay? Okay, so I put a note, okay, and also I mentioned this, right, for batch normalization. For this example here, okay, x1, x2, x3, x4, not the sample, but x1, x2, x3, x4 are the features. They are the features, okay? By color, they are the feature. And for this case, we only have 3 samples, okay? We have a batch of 3 samples, okay? So for batch normalization, we do the normalization for each, okay, for each feature. See that? We take the feature 1, we calculate the mean and standard deviation from all 3 samples. But for their normalization, we calculate, okay, the mean, okay, for each sample, calculate the mean along all features, okay, and then we do the normalization, okay. That's what means the normalization will be, okay, we do something like this, okay. Okay, that's the difference and layer, and you can evaluate what might happen for your assignment number 4. Okay, especially I ask Carl to include some test image that contain different illumination, okay, which are quite different from the training sample, and you will see well convolution nets perform better or not. Okay, I just put a note here. It may not be true all the time, but it can be more robust, okay, for the illumination changes. Okay, okay, and this is the Gaussian arrow activation function. Okay, again, just like red rule, but when the x is negative, the value won't be 0. Okay, you will be negative, some negative value, but eventually you will converge to 0. Okay, that's the idea. You can see this a lot, right? Leakage rule is linear, okay, linear increase, right? Exponential is also will be nonlinear increase, okay? But apparently, this kind of activation function is better, right? If x is negative, then this value will becomes negative for a small value, but eventually you will converge to 0. Okay, it's based on a lot of paper. Finally, they all propose this kinds of red rule. Okay, this function for that. Okay. Okay, so finally, the up-to-date model is called convolutional mixer. Okay, now it takes the patches. Okay, it takes the patches of an input image as the input. Now the idea is quite simple. Okay, basically it does not have many changes of the deep learning architecture. But the idea is like this. First, we have the input image. This is the input image. Okay? Not the feature map, but the original input image. Then it divided into patches. Suppose this is image size is m by n. Then if we have a patch, up size is, let me see, what do I use? Oh, is p by p, okay? The size is p by p, okay? The size is p by p, which means what? for our case here, the size will be P, okay? Is P. So the total number of patches are what? M by P times N by P, right? It was the total number of patches. This is the number of patches. Okay, we have this many patches as I mentioned here, okay? You use N by N, okay? You know what I mean? It does not have to be a square, okay? It can be any size of the image. Okay, this is a more general form. But anyway, for this case, you use, suppose the image size is N by N. Now you have the C channel, okay? Suppose it is a color image, then C should be equal to 3, okay? Equal to 3. Now, we can change the channel from C to H, okay? Depends on how many filter, okay? N, okay? H here will be number of filter, okay? Number of filter. Now, you can think of the filter, okay? For the input, the very first layer, the filter for the very first filter is of size what? The filter is of size P by P, equal to the patch. Equal to the patch. Then, and the stripe is P. The stripe is P. You can think of this so-called convolutional mixer. The input we divide it into P by P patches. And you can think of each patch is a filter of size P by P. And then we move the filter every P pixels. So for this case here, then you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You will have 12 patches. That's the idea. Okay? That's the idea. What is the purpose for that? You can find the correlation or spatial relationship between patches. Okay? Because in the original, when you go for the filter, what can you do? Just look for the information in the neighborhood, right? But for this one, you can find the information across a far distance. Okay. So first, the input image, okay, N by N by N, we have a C channel. Now, we go for the convolution. We go for the convolution with a patch of size or filter of size P by P. Now, the user, you need to determine what should be the size, okay? What should be the size? And you will strike by P. So you will have the first filter here, and then this will become the next filter. That's it, okay? So, and then if you have this many of filter, then we use, for this case, we have a H filter, okay? Totally, we use H filter. So we can change the depth here. And then you go for the activation function. Again, you use a Gaussian arrow, and you do the batch normalization, okay? You might wonder what would happen. You go for the layer normalization. You can try out, okay, if you want. And then after that, this is the so-called convolution mixer block, okay, or layer. Now, see that the basic architecture is nothing but, again, a residual net, okay, a residual net, okay. So you do the convolution, okay? Activation function, batch normalization, and here's you bypass. Okay, this is another residual block. Okay, residual block. Okay, so convolution, activation function, batch normalization, and bypass the convolution, and then we add them together. Okay, and then we go for the pointwise convolution, activation function, batch normalization, and this you can repeat this. Okay, the time steps here, it means you can repeat it, this block 1, 2, and many times. Okay, and eventually you can go for the fully connected and perform your performance for classification or for regression or even for segmentation. Okay, that's the idea. Okay, so the only breakthrough or only something new about it is right here, just right here. Okay, it uses a P by P patch as a filter. Okay, of size P by P with a stride of P, so that you can extract a lot of spatial information far away from each other. And then you will go for the convolution to put them all together. That's the idea. Okay, and the otherwise, you can replace this with a residual net or inception or VGG, that'd be fine. But for the proposed convolution mixer, it go for, remember I asked Jen to send you the supplementary material? 补充资料, email you what? To the depth-wise convolution and then pixel-wise convolution. Did you? 有没有拿到？有吧？ Because that's something. Okay. Because it says here. Okay. Anyway, that's the first layer. Okay, the first layer here, and then you will go for the depth-wise. Okay, the depth-wise convolution, and then point-wise convolution. Okay. Just give me one more minute. Okay. I will explain it. So, if originally you have a okay. You have the image with R, G, and B. That's a color image. You want to do the convolution, you can go for 3 by 3. And then the size must be the depth. For this case, the depth must be 3, right? 3 by 3. The total is 27. Now, you go for the depth first. We split it into 3 R, G, and B. Okay? Now, the original, as I mentioned, if it's 3 by 3, then the depth is 3. You need up to 27. But for this one, the filter size for each channel is only what? 3 by 3. 3 by 3. Okay. For this case, you may not find the. But if I need to use 100 here, that will be a lot different. You know what I'm saying? 100. But for this one, there's only 9. Okay, there's only 9. So I separate this so-called depth. This is called depth-wise. Okay, depth-wise. Convolution. Okay, we separate. We don't put them all together. And then after that, we do the concatenation. Okay, we put the concatenation, and we put that back. Okay, we put that back. And then we can carry out the pixel-wise convolution. And the pixel-wise convolution is only 1 by 1. That's the idea. Okay, 1 by 1. For this case, 1 by 1 by 3. Okay? And if you need to change it to 100, you just use 100. Then this is only 300, right? For the depth, 100 is 9. This is only 27. Now, the number of parameters is only 27 plus 300. But for this one, you need up to 2,700 parameters just for this convolution. That's the idea. But the result won't be the same. Okay? It just tries to reduce the computation time. Okay? So it calculates the depth-wise convolution. And then it go for the pixel-wise convolution to find the spatial relationship in each channel. But for the depth-wise convolution, it tries to find out the relationship between different channels or between different R, G, or B color. That's the purpose. But this technique is used in the convolution mixer. Okay, you can find more information from your supplementary material. Okay, let's take a break. Okay.